This is a tutorial on performing simultaneous multiple source function fitting for the cases where you have adjacent sources and you would like to extract the photometry for such sources. In another video, we demonstrated performing curve of growth photometry on a single well-isolated source. Today we're going to do photometry on these three sources, two of which are largely blended, and one of which is somewhat separated, but still it can be included in the multiple function fit. Now we will be fitting using the sub-image region of interest window. And so we will see that there are four options for the function which we would like to fit. You have your symmetric circular Gaussian, your elliptical Gaussian, a circular symmetric Moffett, and your elliptical Moffett. The elliptical, these are increasing number of parameters. So the Moffett, the elliptical Moffett, is the most complex function to fit. It takes a little bit longer, but it is also the most general and generally gives the smallest residuals, and which therefore should be your most accurate estimate at your volume for each source. The volume, of course, of the function being the volume above the background, that is, being the total counts of your source. So just by way of example, this is the function for the elliptical for the symmetric Gaussian. So the functions are a sum over a bunch of Gaussians with different centers. So depending on the number of Gaussians, you have different centers, and they each can also have their own sigma, so their own full width half maximum, or their own sigma decay factor. They each have their own scaling factor or amplitude, but they all have to share a common background for this function to work. So all the functions together share the common background. The common background is added into all of them, but then each source has its own particular Gaussian with its own particular decay factor, sigma, and center. All right, so of course this function would change depending if it's elliptical Gaussian or elliptical Moffett or rotated Moffett. The Moffett is a different form, obviously, than a Gaussian, but that's generally the idea. So you're summing up a bunch of Gaussians or Moffetts at different locations, and so they, superimpose upon each other when they're close and they blend together, but then they share a common background. Okay, so going back to our image, first we need to tell CCDLAB that we want these 3 points to be recognized as sources. So we just take an estimate, take a quick look at the values of the amplitudes here. So we see that the maximum amplitude is 745. And this dimmest source, if we put the mouse cursor over top of this source and look in the bottom of the corner window here, it'll tell us the value at that pixel. So 477 is the minimum. So let's perform point source extraction, and let's perform it on the region of interest only. And these values will probably be sufficient. A minimum pixel value of 55. Well, of course, we know it's much higher than that. A sum of 148, let's just leave it there. That's just a random value that was left there last time. And a source separation minimum of 3 pixels. That should be fine. These look like they're separated by a little bit more than 3 pixels, even though they're blended. And a kernel radius of 2 is fine, so that's plus or minus 2 pixels to perform the centroid. That actually can perhaps be increased to 3 because these are fairly broad sources, it looks like. So with that said, we simply, we can do auto background, and we simply do PSE, and so it says it found 3 sources in this window, as we would expect. And of course, you can adjust these parameters to get the correct number of sources that you think should be there. So now that we have that, we would like to fit the function. So for example, we can just do the circular Gaussian. So CCDLAB will estimate all of the parameters needed in the fit. It will use the amplitude above the background of each source, given each centroid. So we'll estimate that as the starting point in the function fit. It will estimate the full width half maximum, given the kernel radius that you had supplied for your point source extraction. It will estimate the background by taking the median of this whole window, or perhaps it's the minimum. It's either the minimum or median of this whole window is the background. And so basically all we need to do then is hit fit, and it returns fairly quickly the parameters for the 3 sources here. So we have the total volume. So your total volume would be your total source counts. Full width half max, people always want to know. So of course, if you want to do a more complex function, for example, the elliptical Moffett, It does show us the form, the basic form of the equation here. Of course, we are summing together this part, and the background is the same for each source. It's universal for all the sources summed together. And so we get some slightly different values here. Now you can actually view these fits by clicking View Fit, and this will call up your MATLAB engine. So you have to have MATLAB installed, just the MATLAB component runtime, so you don't need a license for MATLAB. You just need the runtime, which is free to download. It does take a moment to boot it up the first time, but once it's booted up, it's here. You can see it. So here's your data. This is a surface plot of your data, so you can see that these two sources are blended together. Here's a third source slightly offset. Here's the fit, the Moffett elliptical fit. So that's looking like a nice fit because it looks identical. Here's the data in the fit overlay, which sort of gives you a bit of an idea of how the fit is doing. You can see if perhaps there's some regions here the fit is too high, whereas here the fit is too low compared to the data, but that's what you would expect because you never have a perfect Moffett or a perfect Gaussian in actual data. And then this window here shows you the residuals. Okay, so the residuals have an amplitude of about 15 counts. So if we were to compare this to, for example, the circular Gaussian, we see, in fact, a lot worse residuals, much higher amplitude, and you can see that the peak is underfit. The middle, or what would you call that? Just the mid part of the wings, or the decaying factor here is underfit, and then the wings are overfit again. So you have much worse residuals there. So in our case, you would probably want to go with the most general term, which is your elliptical Moffett. So in any case, so that was our circular Gaussian fit. Here's our elliptical Moffett fit. So I think that you can save these into a comma delimited file, so you can put that into Excel or a tab delimited text file. You also just have it here, which you can copy, Control C, or do whatever you would like with. And so there you go. That is your basic strategy or implementation of simultaneous multiple source function fitting. In any case, that is the technique. Thank you. Bye-bye.